Now we have some special matrices that we need to account for. A square matrix is one whose dimensions are equal. So we have a matrix M by P, where M is equal to P. So this would be like a 2 by 2 matrix, a 3 by 3 matrix. It forms a perfect square. A zero matrix is a matrix whose entries are all zero. And usually we denote this as a capital O. A diagonal matrix is a square matrix whose entries on the diagonal are not zero, but every other element is zero. An identity matrix is a square diagonal matrix whose diagonals are all 1 and every other element is 0, and we'll denote the identity matrix as a capital I. The term symmetric matrix is a matrix where its transpose is identical. So in other words, matrix A and its transpose are identical. Here we have a few examples. A is a square matrix. It's a 3 by 3. The zero matrix, O, is a square matrix with all zeros. Matrix D is a diagonal matrix. All the entries on the diagonal are not zero, and all the other entries are zero. The identity matrix is a diagonal matrix where every entry on the diagonal is 1. And here we have M and M transpose, which is a symmetric matrix because it yields itself. Now, a little bit more advanced in terms of linear algebra is this concept of linear independence. So a set of vectors is linear dependent if you have a constant can be found such that we can multiply that constant by each entry and end up with a 0. If no constants can be found satisfying the equation above, then the set of vectors is said to be linear independent. So if we take a look, in the matrix A, if we multiply the top row by -3, we would end up with a multiple of the second row in the matrix. So therefore, this is linear dependent because rows 1 and 2 are multiples of -3. B is linear independent, and the reason is because we cannot find a multiple that will work to satisfy the equation above. And the same holds true for C. C is linear independent. Now, the rank of a matrix is equal to the number of the linear independent rows or columns in a matrix. So we can show that the number of linear dependent rows equals the number of linear dependent columns, but we're not going to prove that here. Therefore, the rank is going to be the smaller of the two, or in a square matrix will be equal. So therefore, in a square matrix, which will be most of the matrices that we will work with, especially because we're dealing with a covariance matrix, the rank is going to be equal to the number of linear independent rows or the number of linear independent columns, the smaller of the two. A matrix is said to have full rank if the rank is equal to the smaller of the number of rows or columns. If matrix is 2 by 3 and the matrix has a rank of 2, then the matrix has full rank because it equals the number of rows. So in the case of A, we had said originally that it is not linear independent, but the number of linear independent rows is actually 2. And so therefore its rank is 2. In the case of B, we have 2 rows that are linear independent, so therefore its rank is 2. And the same for C.